Hi, my name's Dr. Colin Campbell. I'm a senior research scientist here at Meter Group, and today we're going to be talking about water content. When we use a sensor to make a measurement in the soil, we just get an output of the sensor. Usually this is in something like millivolts. And if it's not a first principles measurement, which these are not, usually we create a relationship between the output of the sensor and the volumetric water content. So the water content is some kind of function of the sensor output. And now that probably shouldn't surprise you. That's how most sensors work. So I've shown you this calibration curve, but unfortunately, other things affect this calibration. Things like soil salinity, soil type, temperature, and bulk density. If we looked at what that did to our curve, that may make our curve be higher or lower than our calibration line. So not all sensors are created equally in terms of their ability to ignore these things like soil type and soil salinity. One of the things we've been doing over the years is developing the meter sensors in such a way that these have less and less impact on the measurements. The Teros 10, 11, and 12 are now sensors that are almost insensitive to these challenges in the soil. If you want to read more about it, go check our application note on sensor calibration. But another thing we've been working on is what we call complex dielectric with intersection. These are some new sensors we're working on that we're planning to release soon. Now, why are they so important to us? Well, let's talk about it. Instead of simply going from a sensor output to the water content, the complex dielectric with intersection, or CDX technology, does this in a two-step process. First, we take the sensor output and we turn it into dielectric. Once we turn it into dielectric, this has the ability to separate what we call the real and imaginary parts of that dielectric. Why is that important? Well, we can be completely insensitive to things like soil salinity. But we don't stop there. With our dielectric, the real portion that is, we can transfer this over into a new equation where we create a relationship between the dielectric and the volumetric water content. That way circumventing some of the challenges that I just mentioned. I also mentioned this split between the real and imaginary dielectric. What does the imaginary dielectric give you? Well, this is the symbol for imaginary dielectric, and with this we can measure electrical conductivity. Most importantly, this will give us the pore water electrical conductivity along with the real portion of the dielectric, something that we've never been able to do as effectively as now. Some people ask me why they should buy a meter sensor to measure volumetric water content. One of the reasons I give them is we've actually put 25 years of research and science in our sensors. Check this out. When I got here to Meter 25 years ago, we were making the Echo 20, our echo probe that was taken up into the market by a lot of people. Was it the best sensor? No, but it was a good sensor. It was a great way to measure volumetric water content. We simply weren't satisfied with that and soon came out with the EC5 and later the 5TE. But again, we saw ways to improve the sensor and have it last longer in the field and be able to measure the water content more accurately. And so we see this Teros 12, for example, that came out just a few years ago. We're not going to stop there, though. We're going to keep developing and trying to understand these measurements better and better. One of the things people often ask me is what sensor is right for my application. And that discussion really needs you to go over and look at our knowledge base on metergroup.com. So I'm just going to cover it pretty briefly. In sandy soils, life is pretty great. You're not going to have a lot of challenge there, and probably whichever sensor you choose just depends on what kind of measurements you need, temperature, electrical conductivity, along with your water content. As you get into the clay soils, though, you got to be a little careful. This is where calibrations to that sensor output tend to fall down. One of the things we've done with the Taros line, the Taros 10, 11, and 12, is to make sure they're extremely accurate across all soil types. Every sensor we make is heavily tested in our soils lab to make sure they measure well. But one of the things you got to know is if you're going into rocky soils, you got to prepare for that. Maybe a profile sensor like the Taros 54 isn't going to be your best option if you're going to try to pound that into some rocky soils. And finally, if you got some salty soils, kind of like this right here, you got to be aware that can really shift your measurement and cause you errors. Again, in a typical soil, your Taros 11, 12 are all going to work depending on your needs. But if you've got some very challenging soils, you may consider using this new technology, the CDX technology, to try to overcome these with its real and imaginary parts separated. You can get a lot more accuracy out of those measurements.